We're going to be looking at the principles and practices of commercial construction, and it is the 8th edition by Cameron Andrews and Ronald Smith. Make sure you do have the right editions as we're going through these manuals, or you'll be on the wrong page number. I want to talk in general for a minute about this book. Give you maybe some ideas of how to find information. Once again, the key to studying is knowing where to go for different, pieces of information. What would be in this book? What would be in the code book? What would, is likely to be in Walker's? We talked about Walker's being primarily an estimator's book. How much is it going to cost? How many square feet of, shingles do you need? That kind of thing. But this book is about principles and practices, once again, of commercial construction. There is a lot of information in this book. There's a wide variety of general information. Let me give you an idea of a strategy that I employed the first time I took the contractor's exam. I realized that this book had a really good index in it. So if I got a question and I was just absolutely clueless as to where to go, and there was a possibility that it could be in this book, the question didn't direct me to another book, or it wasn't obvious that it was in another book, and I just didn't know where to go, I would start with the principles and practices of commercial construction, because I know that I could pop open that index, and if it was in this book, more than likely it would be in that index. And if it wasn't in the index, then I could go to another book, possibly the Walker's. It's got a good index in it too. So it's all about strategy. So that might be a strategy you want to employ. Well, let's open the cover, and we'll take a look on inside the front cover. There's a lot of formulas there. There's conversions. There is, for instance, it'll tell you that. Let's take a look here. Let's take a look at what we have. We have length. Let's say we want to know how much a centimeter is. This is at the top left on the inside cover. We have a millimeter, we have a centimeter. A centimeter is 0.39 inches. Are you going to need that one in particularly? Probably not, but at least we know we've got some conversions there on the inside of that chapter, inside that cover. I want you to start highlighting on page 6. So let's jump over to, well, actually, not page 6. Let's go to page 5 and page 4. There's a table on page 4 of Principles and Practices of Commercial Construction, table 1.1, that discusses your type of soil and what your allowable bearing strength of the soil is. We have what I want you to highlight is your firm clay and your soft clay, and I want you to know how many pounds per square foot of bearing strength that particular type of soil has. Remember, this book has millimeters and, of course, English measurements. We do want to stay away from the kilopascals, and we want to stick with our pounds per square foot. Another thing about this book is, as I go through it, I'm going to go through the tabbing and highlighting. I'm not going to explain grade. I'm not going to explain elevations. That's done at another section, and I'm not going to go over the math questions. I'm just going to do the tabbing and highlighting. We're going to do the math and those types of things in another module. All right, we're going to be on page 5, left-hand column, about halfway down. The paragraph begins, to control the amount of settlement, it is recommended that the fill material be placed in layers not more than 6 inches thick. So we're going to put fill in. We're not going to put it in more than 6 inches thick, and then we're going to compact it. Now what you're going to find is you go to these other reference manuals, they may have different information. In the Walker's book, it says you can put fill in as thick as 12 inches, but this book says 6 inches. So if they say according to principles and practices, we're going to answer according to principles and practices. We're sampling soil, we're compacting soil, we're excavating and doing things like that. And so on page 6, left-hand column, the first full paragraph says, usually a truck-mounted drilling rig is employed to drill the test holes, from which samples of soil are obtained using special sampling tools. The two most common are the split spoon sampler for soil characterization tests, and the Shelby tube for relatively undisturbed samples. The Shelby tube is a thin-walled cylinder. It's pressed down into the soil at the bottom of the test hole and then raised with a core of soil inside. Let's jump over to page 7 and we'll read paragraph 1 at the top left-hand column on page 7. A hand auger is useful for bringing up samples from relatively shallow depths in soils that are cohesive enough to be retained in the tool while it's being raised to the surface. Paragraph 2 says the use of test pits is probably the best method of examining subsurface soil because it is possible by this method to examine the layers of earth as exactly as they exist. Still on page 7 on the right-hand column, paragraph number 3 says the wash boring method requires the use of water. As a result, the borings are in the form of mud. Any given sample may be a mixture of 2 or more layers of soil, thus a particular stratum may or may not be detected at all. Let's go to page 14. Jump on over to page 14, and I want you to highlight the second paragraph on the left-hand column. We're talking about surface testing. That second paragraph says various tests are available and use specific test equipment for checking the surface conditions of backfill material. The penetrometer for measuring penetration resistance, density equipment to check the in-place density, and moisture testers for testing the moisture content of soil. You know, whenever you see 3 things, say there's three ways to test the surface here, or you're actually testing the soil at the surface. Whenever you see 3 things, this is a prime candidate for what they call a negative question, which is the following is not a method of surface testing. Well, you're going to look here, you're going to find the 3 that are on the test question, and you're going to choose the one that's not here. Let's read on page 15. We're talking about compaction testing here. We have to read the whole paragraph to understand the important concept that you'll need to know out of this paragraph. So let's do that. The testing process begins by obtaining soil samples of the various soils on the site that are to be compacted. In the soils laboratory, these samples undergo a standard lab test known as the Proctor test, developed by R.R. Proctor in the 1930s. Known as the standard Proctor test, it was developed for testing slightly cohesive to cohesive soils. As compaction equipment improved, the test was modified to reflect the greater compaction values that could be achieved. This test became known as the modified Proctor test and is now primarily used for granular soils or gravels. From the test results of each sample, a plot of the dry density of the soil versus the percentage of moisture content is made, producing a bell-shaped curve. This is what's key. The peak of the curve represents the maximum dry density and the optimum moisture content of the soil. You may not understand a word of that paragraph, and that's not a problem because all we have to do is answer the test question correctly, and I want you to make sure you can find that last sentence in that paragraph.
Under compaction test, referring to compaction test.
Let's jump over to page 21. Now 21 has a lot about site layout, and it has a lot about elevations. Now there'll be another module where we talk about elevations, so we won't actually do an elevation as we go through this chapter, but there are some terms that you need to be aware of, so we will be doing some highlighting. Let's look on the left-hand column, second paragraph. Go about halfway down that paragraph, and I want you to find benchmark. This is on page 21, left-hand column, second paragraph, halfway down that paragraph. A benchmark is a point of known elevation. Skip about 4 lines, and we're told a datum point is a reference point, usually given an arbitrary elevation. As we go down that column, there's a discussion of surveying instruments, and I want you to highlight at the top right column on page 21 the first full paragraph. Three basic types of surveying instruments are available for use in the construction industry: the level, also known as the builder's level, the level transit, and the theodolite or transit. A couple of things here. Remember, if you ever see three things, there's a negative question waiting to happen. Another thing is, know that if they say level, they're meaning builder's level. It tells us right there, the level is known as the builder's level. The level at the bottom of the page. Two varieties of levels are shown in those figures 2.2 and 2.3. What's key here is the level operates in a horizontal plane only. Now this, if they say level, they mean what? Builder's level. It operates in a horizontal plane only. Let's flip over to page 26. Right-hand column, first paragraph, horizontal leveling. Once the instrument is leveled and the laser beam rotated, the resulting plane of light created by the laser can be used for a reference for aligning screeds on concrete floors, pouring concrete slabs, installing suspended ceilings. Let's go to the top right on page 27. Now we're talking about a level transit. Now, for the level transit, it says, besides turning in a horizontal plane, a level transit will also tilt through a vertical arc up to 45 degrees from the horizontal position. Next paragraph, theodolite or transit. The telescope on a theodolite may be rotated 360 degrees in a vertical plane. So that's important to know. If we're highlighting it, you're probably going to want to toss a tab on it, and these are all great pieces of information. These are real easy to find. They take about 30 seconds to answer, and they count just as much as those plan questions and math questions that are going to take you about 30 minutes. Strategy, strategy, strategy. All right. You got to pick and choose the ones that you're going to come back to later. And those might be your plan questions and your heavy-duty math questions. Page 35, left-hand column, we're talking about something called collimation. Left-hand column at the bottom, second paragraph under the bold heading of collimation adjustments. Collimation of a leveling instrument means checking and adjusting to ensure that the line of sight through the telescope is parallel to a true horizontal plane. And you've got 8 steps there. I'm not going to read them all to you, but if they ask you about the steps of collimation someday, you'll know right where to go. Let's go to page 37 on the left-hand column at the bottom. We're talking about elevations. The difference between the rod readings at two locations will be the difference in the elevation or grade. We're going to roll several pages back. Like I said, they have an explanation here of how to shoot grade, but I'm really not crazy about the way they do that. We'll be talking about how to shoot grade here, and you're going to definitely need to know how to do that, but we're doing that at another time. Let's take a look on page 48. Running grades on page 48 at the bottom, left-hand column. Sometimes it is necessary to run grade lines that have a uniform rate of rise throughout their length on a construction site. In standard units, grade lines are usually expressed as a given number of feet of rise per 100 feet of length and are usually expressed as a percentage. For example, a 1% grade means there is a rise for 1 foot of every 100 foot of horizontal distance. If you can get that concept down, you can answer just about any grade question. All right, a 1% rise, a 1% grade. There's a 1% rise for every 1 foot, by the way, for every 100 feet of horizontal distance. Let's go to page 70. Let's go to page 70. In the right-hand column on page 70, there's a table 3-1, soil swell percentage. You have silt, clay, sand and gravel, and so forth. We're told in this table that clay is going to swell approximately 25%. They also have a very similar table in the Walker's book. So one of our challenges is that there's going to be similar information, overlapping information, and even conflicting information from book to book. So you're just going to, if they say according to principles and practices, of course, we'll use this table. Next, just below the table, we'll highlight here when dealing with earthwork calculations on the volume of material. The volume of material is related to its condition or state. Highlight this. Soil in its undisturbed state or in its in-bank condition has a volume termed its bank cubic yards. If they ask you how many bank cubic yards there are in a pit, you do not adjust for swell. That's just the way it sits in the ground right there. Okay? Over the next several pages, or the next couple of pages anyway, they do a calculation on how to figure out how much soil that you're going to pull out of a pit. On another module, on our math module, we'll talk about excavations, and we have a much simpler way of explaining this. So I wouldn't spend a lot of time looking at how they calculate how much fill you're going to be pulling out of a pit. Let's go to page 72, and we'll look at the right-hand column. We're going to be talking about some cranes in the right-hand column on page 72. Let's go to the third paragraph. This is the last paragraph on page 72. Two basic types of cranes are commonly available for use on the construction site. You have the stationary crane and the mobile crane. As we go to page 75, we're going to highlight in the left-hand column, and we're going to highlight that first paragraph, but we're not going to highlight until we go about halfway down that paragraph. I want you to find this sentence halfway down, a little more than halfway down, that first paragraph on page 75. Tower cranes have one advantage over mobile cranes. The operator's cab is placed at the top of the tower, providing the operator an unobstructed view of the construction site. Let's go to crane principles at the bottom right on page 75. I want you to highlight the last sentence fragment at the bottom of page 75 on the right. The sentence says a gantry is used, go to the next page, to provide better boom support. That's what a gantry is for. If you don't know what a gantry is, flip over to page 78. In the right-hand side, the bottom diagram shows you a high gantry. There you go. So now you know not only the definition, but you know how to spot one on a diagram should you see that. Let's take a look at page 91. Let's jump over to page 91. Choosing excavation equipment. A number of factors must be considered when deciding what type or types of excavating machinery will do the job most efficiently. Make sure you can find this little ditty of information right here. The first point to consider is the volume of material to be removed. Now, let's go to the next paragraph, and we're told that the disposal of the excavated material may influence the type of machinery used. If it can be deposited in a spoil bank at the site, one machine may do both the digging and depositing. The distance from the excavation to the spoil bank is also a factor. Next paragraph, the type of soil to be excavated will influence the kind of equipment selected. So there's a lot of things going on there. And let's look at the top of the next page on page 92. Make sure you can find this. Many factors have a bearing on the type and size of machine that will be considered. The major considerations are, there they all are, make sure you can find them, that's very important. The rest of the next couple of pages is a very complicated explanation of what they call cycle time. We're not going to spend a lot of time here worrying about cycle time because we're going to do a much simpler explanation of this concept when we do another module on our math calculations. So let's jump over to page 94. And on page 94, once again, we have a table. It says hourly shovel handling capacity for shovel dipper sizes. So you have a shovel size, say a 1 yard shovel. If we're going to be moving moist loam or sandy clay, it's going to be 205 cubic yards. And what is it? Per hour. That's going to be our production. What in the world is loam? Does anybody have any idea what loam is? I first heard that term, had no idea what it was. What I suggest you do when you hear the term loam, just think of dirt. I hate to admit it, but I was at home one day watching the Home and Garden TV station, and they actually used the term loam, and they explained what it was. It was soil that was equal parts clay, sand, and silt, and all that mixed together produced loam. There you go. Let's go to page 110. We're going to go to page 110 and see what we got on page 110. Dynamite. Page 110, left-hand column, last paragraph. Dynamite is produced in various grades, depending on the percentage by weight of nitroglycerin the soil contains. Thus, a 30% grade contains 30% nitroglycerin, 60% nitroglycerin, and so forth. This does not mean that 60% dynamite is twice as strong as 30% dynamite. In fact, it is only about 1 1/3 times as strong. Let's jump over to page 137. What in the world are they talking about here? Well, guess what? This is a piling question. This question is about how much weight a pile will support. And once again, they do a very complicated, they make something that is somewhat straightforward very complicated. Engineers wrote this book, and it's not made for the layperson to figure out these calculations. So we do a much better job of that when we talk about math. So we won't do the calculation right now, but there are some things I want you to highlight. On this page, on the left-hand column, there's a paragraph, the first paragraph, and I want you to try to go about halfway down that paragraph and highlight this sentence. The average compressive bearing values for gravel soils range between 5 to 6 tons per square foot. On page 138 and 139, there's a discussion of wood piles. On the right-hand column, under wood piles, go to the second paragraph. Pile lengths are available in increments of 12 inches. The minimum tip diameter is normally 6 inches, and the maximum butt diameter for any length is 20 inches.
138.
On page 139, there's numbers 1, 2, 3, and 4. Just above those numbers, it says some advantages of wood piles are as follows. Make sure you can find all of those. That's very important for you to find. They have an indefinite life expectancy below groundwater, below level. They're light, it says. Apparently the person who wrote this book never tried to pick one up. In many areas, they're available, readily available, and they produce greater skin friction than most other piles. There we go. Let's jump over to page 144. We're still talking about pilings, and many times you'll place pilings together, close together in order, and then put a concrete cap on top of them and to create a foundation. And you have to start reading at the bottom left on page 144 because it discusses how far apart you should place those pilings. The paragraph begins, first, it is generally recognized that when a number of piles are driven close together, the load-bearing value of each is reduced. As a result, a number of building codes have established a minimum center-to-center spacing for grouped piles. These vary from 2 foot 6 inches to 5 feet, with the latter considered less desirable. And once again, I think that's a mistake. I believe that should say the latter is more desirable because the further apart they are, the stronger they are individually. Let's go to page 147, right-hand column under caissons. And I want you to highlight the last two sentences in the right-hand column of the first paragraph under caissons on page 147. The sentence reads, strictly speaking, a caisson is a shell or box or casing that when filled with concrete will form a structure similar to a cast-in-place pile, but it's larger in diameter. Over the years, however, the term has come to mean complete bearing unit. Let's go to page 149, cofferdam, right-hand column, last section, first paragraph under cofferdam. Although caissons and cofferdams fulfill the same general function, a caisson is a permanent structure used for protection while excavating and as a form for concrete, whereas a cofferdam is a temporary box-like structure used to hold back water or earth while work is being done inside it. It is later removed. Let's see what we got on page 164. We're no longer we're getting into a paragraph, a chapter 6 here, which discusses formwork of concrete. So we're going to be switching gears to a different topic here, and we're going to be talking about formwork and other issues regarding concrete. There's some pretty interesting stuff in this chapter, and I want you to be able to read some of these tables. We're going to talk about these tables here. Let's look on page 164. 164, left-hand column, third paragraph. Now, we're talking about formwork, and we're talking about deflection in the formwork. Typical deflection limits for the various components are usually a maximum of the span divided by 360, but not to exceed a 1/16 of an inch for sheeting and a 1/4 of an inch for joists and beams. Okay, so that's your deflection limits for concrete formwork. Let's look under formwork loads. Right-hand column, page 164, formwork loads. First paragraph, drop about halfway down that paragraph and see if you can find this sentence. Normal density concrete made from natural sand and gravel aggregates has a unit mass ranging between 145 and 150 pounds per cubic foot. That's a nice little number to know. What does concrete weigh? Well, it weighs about 150 pounds per cubic foot. Next paragraph. The American Concrete Institute Committee, 347, recommends a minimum live load of 50 pounds per square foot for work crews and equipment, 75 pounds per square foot if power buggies are used to transport the concrete, to allow for the extra weight of the runways and impact loads. A minimum total load of 100 pounds per square foot for concrete and equipment is recommended, and 125 pounds per square foot if power buggies are used. Top of the next page, on page 65, left-hand column, 5 lines down. Wind forces on wall forms can be based on local codes. However, a minimum of 15 pounds per square foot applied to the vertical projection of the formwork is recommended by ACI Committee 347. 15 pounds per square foot for the vertical projection of the formwork for wind loads. We're going to look at some tables on page 166, 167, and over the next several pages. Let's see if we can decipher what they're talking about here. On page 166, there's 2 tables. You can disregard the second table because that's in metric, and we're not going to worry about metric. So they're the same table, but the top one is in English units, the bottom one is in metric. So let's take a look at the top one. Maximum pressure for design of wall forms. We're going to build a wall form. There's 2 things that affect the stress, the force that you're going to put on a form. One of them is the temperature outside. Well, why is that? Well, the hotter it is, the faster that the concrete's going to dry, and so it's not going to put, as it dries, it's going to put less pressure on the wall form. The other thing is how fast you're going to put it, your rate of placement. So you have two things on that table. So let's say, for instance, it was 90 degrees outside, and you were placing 5 feet of concrete an hour. So you would have to build your forms to withstand what? 650 pounds per square foot, right?
Yeah.
Okay. Now let's go to the next table. Hold on to that thought. Let's go to the next table. On tables 167, we're building a column. Instead of a wall, we're building a column. It's 90 degrees outside, and we're placing it at 5 feet per hour. How strong do we have to build the form? 650 again, right?
Pounds per square foot.
Yeah. The reason is just because concrete doesn't know if it's in a wall or if it's in a column. So it's the same numbers basically. So let's take that number at 650 pounds per square foot. That's how strong we have to build our form. Now you've got another table, by the way, on page 168, but that's just the metric equivalent of what we already looked at. So we're not going to worry about that. What we are going to look at, though, remember, we have to build our form to withstand 650 pounds per square foot. Let's take a look at page 176. 176 is our English measurements. 177 is our metric, so we're going to pay attention to 176. Wow, what is this all about? Let's see if we can decipher this table. Safe, I'm reading at the top of the table. Safe spacing in inches of supports for plywood sheeting. Now this is, you're gonna put continuous plywood sheeting over 4 or more supports. So that's going to be our criteria for building this formwork. Then this table is telling us how far apart we have to put our supports, and this table is in inches. Now there's, once again, at the top of the table, it tells us the maximum deflection is 1/360th of the span, not more than 1/16th of an inch. Now that was for the plywood. You have a table. This table is broken up into a left-hand side and a right-hand side. There's differences here. And what you have to do is match the question up with the correct side. For instance, if somebody says your plywood is rated at 1930 psi, see if you can find that. It says F sub B 1930 psi. If they tell you that it's 1930 psi, you're going to use this left-hand side. If they say it's 1545 psi, it's going to be the right-hand side. And they might put the rolling shear, and they might put the E value, but all we have to do, those numbers are going to look real intimidating when you see them, but all you have to do is just match those numbers up to these numbers at the top of each side, and that'll tell you which side of the chart you're going to use. Very intimidating looking numbers, but it's actually very simple. So let us say that somebody asks us about the 1930 psi plywood. That's what we're going to use for our formwork. And our rolling shear was 72 psi, and the value for E is 1,500,000 psi. And this is what we're told. We're told that we are going to put our sanded thickness, our face grain of the plywood, perpendicular to the span. So that's going to be the right-hand side of the left-hand half of the table. Hopefully you see where one is parallel and one is perpendicular. So we're going to put our sanded thickness face grain perpendicular to the span. Are you with me?
Where?
How strong do we have to build our forms?
600.
650 psi. So what do we look on the left hand side, and where do we have to go to? 700. So we follow 700 along, and let's say we're told that we are building this particular formwork with 1-inch plywood, sanded thickness, face grain, perpendicular to the span. What is our spacing of our supports? 12 inches. So every foot we need to put a support under those circumstances, right? And by the way, that is your stringers and your wales. So both supports, vertical and horizontal, are going to have to be 12 inches on center apart. That's how you read that table. It's a whole lot to go through, and it looks very complicated at first, but it's actually not too awfully bad.
Question.
One second, before you go too far though, make sure there's a difference between the tables on 176 and 178. There's actually, how many sets of tables? There's several sets of tables that's discussing the same thing. So I want to show you something here. And I want to highlight this because I want to make sure you could know all this stuff and get the question wrong for this issue. 176 and 177, look at the top of, on 176, the heading of the table, safe spacing in inches of supports for plywood sheeting, continuous over. Make sure you highlight in a different color or underline 4 or more supports. Because if you look at that same thing on page 178, it's a similar table, but what does it say there? 2 or more supports. Page 180, 3 or more spans. All right. So this is and this is a single span on page 182. So make sure that your test question that you're answering fits exactly to what the heading of that particular table is telling us. We're going to pick up on page 205. We're still talking about building forms. We got a pretty big jump there. We're going to jump over to page 205. And on the left-hand side, the left-hand column on page 205 at the bottom, we're told that wall forms are made up of 5 basic parts. You have sheeting, okay? You have studs, you have wales, you have braces, and then you have ties or spreaders. So make sure you can find the 5 parts of wall forms. Page 224. Page 224. Let's look in the right-hand column and let's see if we can read that first full paragraph on page 224. We're talking about shoring and reshoring. Okay. Shoring and reshoring semi-cured slabs allow the contractor to transfer the construction loads through the shores without affecting the freshly poured section. So what you're doing is you're pouring a floor, and then it's not going to cure completely, but you're going to be pulling braces out from underneath it and moving up as you go up the building, right? Because it's 28 days before it's fully cured, and you're not waiting 28 days for every floor. So you're moving these shores up from floor to floor. Now, this is what is very interesting. As we read on, it says the amount of shoring and reshoring depends on, 1, you might want to hit these in different color highlighters or do something to let you know that there's a few different things here. Number 1 is the strength of the partially cured slabs. Number 2, the amount of load that is to be transferred to each slab. And number 3, the rate of advance that the contractor wishes to achieve. I got to tell you, if I got a negative question and it said which is not an issue with regard to shoring and reshoring, I would say I would choose safety to be more important than the rate of advance that the contractor wishes to achieve. But according to the principles and practices of commercial construction, you're going to answer exactly like they tell you in the book. Anyway, on page 227, you've got some pictures there. All we were looking at on page 227, all that I'm concerned about is these pictures where you have something called a flying form. When you're building a structure that has a very uniform type of construction from one floor to the next, you don't have to rebuild your form every time. You just fly it from one floor to the next with a crane. Gives you an idea of what a flying form is there. Let's jump over to page, let's see, I think we're going to be on page 251. Page 251. This is a table that takes a minute to explain what we're talking about here. The effective temperature on the strength of concrete. So, if you've done any concrete work, you may note that when it gets really, really cold outside, it takes a long time for the slab to cure, right? In North Florida, where I'm from, it takes, those cold days, it may not cure right away. So those concrete guys got to work all day long on those slabs. So let's look, and we also ought to know 28 days is your typical normal concrete time that achieves, full strength. So what the table 7-8 says, the effective temperature on the strength of concrete. Now where we start is as our baseline. It says the crushing strength of 1-2-4 concrete. So I guess that's 1 cement, 2 sand, 4 rock, expressed as a percentage of a 28-day strength of normal Portland cement concrete. Let's take a look at what they mean. Let's look at a couple of numbers here that'll kind of give us an idea of what we're talking about. Let's look at normal Portland cement. Normal Portland cement at 28 days under normal temperature, what's our percentage? 100. So that's our baseline, right? Now if it was 36 degrees in 28 days, it would only be what percentage? 92%. So we may have to use something called high alumina. If we used high alumina after 1 day at a low temperature, 36 degrees, what percentage of full strength would it be? 54. So that's the way they're reading that table right there. Very important table for you to be able to find. Let's go to the top of page 252 on the left-hand column. We're going to find slump test. It's made to ensure that the concrete has the flowability required for placing. A slump or a slump range will usually be stipulated in the specifications. The test is carried out as soon as a batch of concrete is mixed. Standard slump cone and tamping rod are also required. The cone is made of sheet metal, 4 inches in diameter at the top, 8 inches in diameter at the bottom, 12 inches high. The rod is 5/8 of an inch, bullet-nosed rod, approximately 24 inches long. The cone is filled in 3 equal layers, each tamped 25 times with the rod. So how many times do you tamp a slump test with the rod? 75 times. There's 3 layers, each tamped 25 times. There you go. When we get to design and control the concrete mixtures, if you haven't looked at that already, there's some really good pictures in there. And it basically tells you the same thing. But believe it or not, these 2 books, they do vary a little bit in how they tell you to do these things. But what we're going to do is we're still talking about concrete here, and we're going to look on page 256. And we're going to read right at the very top of the page on the left-hand side, and we're going to be told that under usual conditions, no more than approximately 10% of the mixing water should be placed in the drum before the dry materials are added. That's page 256, first sentence on the page. You're going to put 10% of the water in first. Let's flip over to page 259. First full paragraph, left-hand column, page 259. Concrete pumps are used to transport concrete under pressure through some type of piping system. Pumps are of three types. You have your piston pump, your pneumatic pump, and your squeeze pressure pump. Gives you a little discussion of a piston pump there. I want you to highlight the next paragraph, your pneumatic pump. It consists of a pressure vessel and equipment for supplying compressed air. It's taken into the pressure vessel, intake valve is closed, and so forth. Make sure you can find these. Very quick, easy questions to answer in your life, and you'll be happy if you can find these. On page 261, we're going to talk about concrete transportation on the right-hand side. We're going to look at the fourth paragraph. This is the last paragraph in the right-hand column on page 261. Transit mixed trucks are available in sizes ranging from 1 to 12 cubic yards of capacity. Each batch of concrete should be mixed at not less than 50 or more than 100 revolutions of the drum or blades at the prescribed rate of rotation. Any additional mixing should be done at the designated agitating speed. So when you see a truck going down the road, that's the agitating speed, not the mixing speed. Concrete should be delivered and discharged from the truck mixer within an hour and a half after the introduction of the water to the cement and the aggregate. Let's go to page 262, right-hand column, first full paragraph. Concrete placed in forms must never be allowed to drop freely more than, says here, 1 meter. We're going to know that's about 3 feet. And that's what this book says.
260.
Page 262, right-hand column, first full paragraph. Let's go to page 264, right-hand column, second paragraph. The correct placing of concrete includes proper consolidation to ensure that no pockets or spaces remain unfilled, and that the face of the formed concrete has been made as smooth as required by specifications. The compacting or consolidation is done by means of puddling spades or vibrators. We gotta jump a pretty good bit here. Let's see where we're gonna go first. Let's go to page 304. I'm going to be on page 304. At the bottom left, now we're talking about a different chapter here. If you'll look at the very, very bottom of page 305, it'll tell you what chapter we're in. We're in the structural timber frame chapter now. We're not talking about concrete or anymore. So on the bottom left on page 304, once again, the paragraph is titled Materials Used, and it begins, laminated timbers are widely recognized as being among the finest permanent structural materials. They are made from kiln-dried stock, mostly Douglas fir, southern pine, and so forth. We're still talking about those laminated timbers, and we look at the top of page 305 on the left-hand side. Tests have shown that adhesives can be made to develop the full strength of wood, and that time alone does not affect the strength of the joint when the proper adhesive is used for the given conditions. For laminated members that are protected from appreciable amounts of moisture and relatively high humidity, case-in glue is satisfactory. When laminated members are continuously immersed in water or subjected to intermittent wetting and drying, such as exterior exposures or in buildings where high humidities are encountered for long periods of time, highly water-resistant adhesives such as phenol resorcinol or melamine resin glue should be used. Let's jump over to page 354. 354. Once again, we're not in that same chapter. We're not in chapter 8. We're in chapter 9, where we're talking about a reinforced concrete frame. So this is about skeletal frames. These are steel frame buildings here. And on page 354, let's see here. Page 354 on the left-hand side, the last paragraph, we're told that curtain wall panels are units that carry no loads except wind load. Curtain walls only carry wind load. And just an interesting thing from my perspective, on page 356, on the top left-hand column, that's actually in my hometown right there, Jacksonville, Florida. That picture at the top left, that's the Gulf Life Tower. And you got the Prudential building in the back there. That's when they were building the Gulf Life Tower. At least that's what it looks like to me anyway. Let's see. We're going to go to page 361 and talk a little bit about tilt-up construction. Tilt-up construction. Left-hand column of the top. Tilt-up construction is a technique for producing precast wall panels for 1- or 2-story buildings at the job site. The book tells us 1- or 2-story buildings. You may have worked on 3 or 4, but we're going to go with what the book says on test day. Structural steel frame building begins on page 365. And we are going to look at a table on page 367. We may have talked about this before in a different section, in a different module, but here's a very important piece of information that I want you to be able to pull off of this table. The left-hand column is how these beams are designated. It says W shape. I call them I-beams, but it talks about W here, so we'll go with W. It says W14 by 132. Well, what does the 132 mean?
You explained yesterday that refers to weight.
Weight per linear foot, right? And look at that table. Go all the way to the middle of that table, called the middle column of that table. What do you see?
Nominal weight per foot.
And what's the number?
132.
132. There you go. That's the number. 1/3. So the second number is always 1/3. Is always the weight per linear foot. That's going to be something you may need to know when you're looking at some plans and trying to figure out how many tons of steel you're going to have to order.
Or the W, the height or the width, I forget.
Let's look at the W. The W relates to what they call the depth. If you'll see the 14, all those are W by 14, and you'll see that they are pretty close to 14 inches in depth. They vary slightly because of the fact of the thickness of the steel, but for the most part, if it says 14, they're about 14 inches in depth. All right, we'll move on here. We will move on. We'll flip a few pages, and we'll see where we're going to highlight next. We will highlight on page 377. The only thing I really want you to find on this page is the diagram at the top. And I want you to note there's a caption in that diagram that reads, "Rod bracing provides longitudinal stability." And that's diagonal bracing that they're doing there, and it provides longitudinal stability. We're getting close. Bear with me. We won't have much more in this book. But there's some stuff here on page 385 that if you can find it, it'll take you 30 seconds to answer this question, and that'll give you a little extra time to answer one of those long math questions or plan questions, because we're talking about bolts on page 385. And on the right-hand column, the first full paragraph, we're told that the A307 bolt is a standard unfinished or machine bolt. It is of relatively low strength and so on and so forth. The A305, A325, sorry, find the A325. Talks about that. It talks about the A490. If you have three types of bolts, remember what I said. If you have three of anything, watch for that negative question. Which of the following is not a type of bolt used in structural steel framing? Yeah, be careful. Next paragraph. Two types of bolted connections are used in structural steel connections. You have a bearing connection and a friction connection. Those are your two types of connections. On page 386 in the right-hand column, last paragraph, we're talking about welds. Last paragraph, two types of welds are most often used in welded connection. By the way, that's fillet weld. That's the way you pronounce that. You have a fillet weld, and then you have a groove or a butt weld. Let's go to page 393. We're going to be putting some base plates in. Right-hand column. We're putting some columns up, and we're going to be putting some base plates underneath those columns. And we're told in the right-hand column in the first full paragraph that base plates are set over anchor bolts. They're raised to the correct elevation by using shim packs or leveling nuts. Those shim packs are 3 to 4 inch metal squares ranging in thickness from 1/16 to 3/4 of an inch. On page 394, on the left-hand column, in the second full paragraph, we're told that after the bearing plates have been set and aligned, they must be grouted. If you look at the bottom, you'll see that. They put concrete around the bottom of the thing. They grouted them. Good for them. We're back to bolting on page 395. Okay, how do we know we're tightening the bolt to the right specification? Well, on page 395, on the right-hand column, the last sentence on the page, the required force may be applied by using a pneumatic impact wrench with a clutch set to apply the required tension. Nuts may also be tightened by means of a torque wrench. Go to the top of the next column. Another method of checking the tension on bolts is by the use of load indicator washers. So you got three things there. You know what I'm about ready to say, right? I won't even say it. You know it. 397 at the top left. Number 1. Here's a good plan. Do not attempt steel erection on rainy days. Let's go to page 399 first of all, because I want you to understand that we are going into another chapter, and we're going to be talking about floor systems starting on page 399. And I want you to highlight on page 412. This is floor systems and industrial flooring. We're on page 412, and we're going to read that paragraph on the left-hand side. Straight leg pans are supported by nailing them to the sides of the joists with double-headed nails. There you go. Let's jump over to page 426. We're going to be putting down some flooring on page 426. We're going to be putting some epoxy on some flooring. And on the left-hand column, the last full paragraph says, two types of floor topping can be made with epoxy. Kiln-dried, salt-free, sand, Portland cement may be mixed, and so on and so forth. You can read the rest of that paragraph, but I'm going to drop down to the last sentence. I want you to highlight the last sentence in that paragraph. Mixes should be limited to 100 pounds. Batches. Mixes should be limited to 100-pound batches because of the limited pot life of the mixed topping. We're going to get to jump all the way to page 500 and, let's see, 511. page 511. Chapter 14, we're talking about curtain wall construction on page 511, left-hand column, last paragraph. To ensure proper performance of a cavity wall, its design and construction must be carefully considered and executed. The minimum width of the cavity must be 2 inches. Let's go to page 533. 531 begins building insulation. So how are we going to make these buildings energy efficient and insulate them? Well, and we also have to fireproof them and that type of thing. So on page 533, we're going to highlight on the left-hand column about fireproofing. 2 material designations are recognized by fire codes when dealing with fire-resistant ratings of buildings assemblies: non-combustible and combustible. Non-combustible materials are mineral-based and include concrete, asbestos cement, gypsum plaster, glass, and natural rock such as slate, sandstone, and marble. Combustible materials are those that contain or are formulated from animal or vegetable matter. Let's go to the bottom of page 533. Let's read that paragraph. The amount of fireproofing that is applied to a structural section depends on the fire resistance rating required and the type of material that is to be protected. Materials in general use for the protection of a structural steel frame, for example, include regular and lightweight concrete, cellular concrete, gypsum wallboard, plaster, and sprayed-on mineral wool. We're getting close here. Let's go to page 539. Remember, this chapter is discussing building insulation, so I want you to highlight on the bottom left on page 539. Let's go to that second paragraph in that column. A well-constructed and well-insulated wall will ensure that the dew point temperature occurs at a point in the wall section where the resulting moisture can be eliminated. The best scenario, of course, is to have the wall constructed in such fashion so the dew point is never reached. However, this may not be practical. The use of an appropriate arrangement of insulation, air vapor diffusion retarder, and air barrier, along with the use of mechanical equipment to control humidity levels and air pressures, is the current approach to obtaining optimum thermal efficiency. Through hard experience, it has become evident that the wide brush approach to building an envelope design is no longer adequate. Page 565. Real simple little deal I want you to highlight on page 5-65. You have a diagram at the top of page 5-65, and it's got a glass door up there. It's got a door. It's got a commercial door, actually. And it talks about where you're going to put the hinges. Highlight the note. In some areas, hinges are located 9 inches from the top of the door and 11 inches from the bottom. The diagram showing 5 inches from the top and 10 inches from the bottom. Page 595 is the index. And I got to tell you, this is the best index, I believe, of all the manuals that you have. And that's one reason I was telling you, if there's a possibility that the question might be in this book and you don't know where else to go, pull that baby out and see if it's in this book. If it's in this book, more than likely you'll find it in the index. And if not, maybe jump over to Walker's. That's got a good index too. Maybe if it's a concrete question, if it's a heavy-duty concrete question, about the mixture of concrete and what goes into it, it might be in the design and control of concrete mixtures. Either way, you're going to pass.